Today on Macaulay Math, we're finding limits. Intro. Hello, I'm Professor Macaulay, and this is Math 200, Calculus 1, Lesson 2 on finding limits. Our goals for today, we are going to estimate the limit with a numerical or a graphical approach. We're going to learn the ways that a limit can fail to exist. And we're going to study the formal definition of a limit. What is a limit, you ask? Well, let's start with the demonstration. As an example, let's say you and your friend want to meet for a burger at the new restaurant, Macaulay's Burger. You are coming from the west and your friend is coming from the east. If you both follow the path, you both arrive at the same point. In this case, the restaurant. In calculus, we think of the restaurant as the limit, the place we get to when we examine the function from the right and from the left. But what happens if the Death Star comes along and blows up the restaurant? Both cars can still get to the same point even though the restaurant no longer exists. This is a very important concept for limits in calculus. The existence of the limit is not dependent upon the existence of the point that we are trying to get to. As a second demonstration, let's look at this graph. From the last demonstration, let's imagine that instead of a road, we have a function. And we want to know what the limit of that function as x gets close to 5. Just like in our last demonstration with the cars, as we inspect the graph from the left and the right and get closer and closer to 5, the function tends to go, in this case, to 4. That is the basics of limits. What does the function tend to do as we get closer and closer to 5 from the left? The function tends to point to 4. And then as we come in from the right, the function also tends to go to 4 as the x gets closer to 5. Since both the green arrow and the red arrow are pointing at the same value, in this case 4, we can say that the limit is 4. Now, suppose that there is a hole in the graph at the point 5, 4. Does this change the limit? That answer is no. Just like in the last example, as we come in from the left and the right, the function still points to 4, and the limit therefore still exists. This is an extremely important concept of limit. The existence of the point at the given x value is not required for the existence of the limit at the given x value. So what would it take for a limit not to exist? Well, let's say that the part of the graph of the right of x equals to 5 is translated up 2 units. Now as we come in from the right and from the left, the function points to 2 different values. Thus, in this case, the limit does not exist at x equals to 5. To finish this demonstration, we must note that there are other ways for the limit not to exist at a point. This is just a simple example. So what is a limit? The limit L of a function f of x at a given value c is the value that the function approaches as the independent variable gets arbitrarily close to the given constant c from both sides of c. The notation for this is the limit of the function f of x as x approaches c is L. This is how we read this notation. Unfortunately, the term arbitrarily close is too vague for this to be a formal definition. Let's talk about what a good formal definition of a limit. Let f be a function defined on an open interval containing c, although the function not be defined at c, with L being a real number. The statement, the limit of f of x as x approaches c equal to L, implies that for any epsilon greater than 0, there exists a delta greater than 0, such that if 0 less than the absolute value of x minus c less than delta, then the absolute value of f of x minus L is less than epsilon. So what does that mean? Let's look at another example. The formal definition of the limit can be summed up in this demonstration. Here we have a continuous function f represented by the blue curve. The goal is to find the limit for some value along the independent axis, which we will label C. This limit we will call L. The delta epsilon definition basically says this: if we want f of x to be within epsilon units of L, then we must pick our x somewhere within delta units of x. So why is this definition better than the formal definition? Well, that is because this definition defends any challenge to where the limit should be. If I am defending my choice of limit, I allow you, the challenger, to pick an epsilon, and I can defend my choice of limit by giving you an appropriate delta. The existence of a limit. For a limit of a function for f of x to exist at x equals to c, number one, both the left and the right sided limits must exist. 2, both the left and the right sided limits must be the same. 3, the function need not be continuous at x equals to c. Note, the existence of f of c is not a requirement for the limit to exist. This aspect of limits makes most of calculus work. To prove a limit using the formal definition, you follow an epsilon delta proof process. We are going to only use this for simple linear functions, as we won't be using the delta epsilon process anywhere else. But if you take a higher level calculus class, you will see this again, and it's good for us to at least introduce it. To use the formal definition of limit to prove the limit of f of x as x approaches c is equal to L, we're going to set up an if-then statement. And it's this if-then statement. If the absolute value of x minus c is less than delta, then the absolute value of f of x minus L is less than epsilon. What we're going to do is algebraically find a relationship between epsilon and delta by starting with this second part and working towards some expression that has x minus c and a relationship between delta and epsilon. Then we will formally start with a hypothesis of the function, the absolute value of x minus c is less than delta, and work towards the conclusion, the absolute value of f of x minus L is less than epsilon, to prove that conclusion. So let's do an example. First, we want to use the formal definition of limit to prove the limit as x goes to -2 of 4x plus 5 is equal to -3. And so what we'll do is we will let c equal to -2. We will let f of x equal to 4x plus 5. And we will let L equal to -3. All right, and so then we need to set up the statement that we're going to prove. If 0 is less than the absolute value of x minus c less than delta, then the absolute value of f of x minus the limit is going to be less than epsilon. So now we're going to substitute the values that we know. By substituting in, we'll get 0 less than absolute value x, and then it's minus -2. So we're going to put a +2 there, less than our delta. Then, and our f of x is this expression, so we'll say it is 4x plus 5, and then it would be minus L. Now L is -3, so we're going to go minus a negative is +3, less than epsilon. And so at this point, we are going to algebraically find a relationship between epsilon and delta. All right, so we're going to start with this epsilon expression, and we're going to try and find a way to link it to this delta expression. So let's start with that. Let's simplify just a little bit. Let's start with 4x plus 5 plus 3 less than epsilon. All right, let's simplify that. All right, so I got 4x plus 8 is less than epsilon. All right, so how is this expression and this expression up here, this x plus 2 expression, related? Well, if I factor out a 4 from both of these terms, I'm going to get an x plus 2. All right, so I'm trying to get an x plus 2. So we are trying to link this expression to absolute value x plus 2. The reason it's x plus 2 is because that's what we came to in the delta expression. If the delta expression was different, this would be different. And we can see that if we factor out a 4 from each of these two terms, we will get x plus 2. So let's factor out that 4. Let's go 4, and we can bring it outside because since it's a positive 4, when I distribute it inside the absolute values, it will stay the same. So I'll have x plus 2 is less than epsilon. Now I'm going to divide both sides by 4. That'll give me x plus 2 is less than epsilon over 4. And now we can say what our relationship between delta and epsilon is. And that relationship is going to be that our delta is equal to epsilon over 4. Now, since we have this, we can write our proof. Now, it may seem like we're just redoing this backwards, but remember, our if-then statement says that we have to start with the delta expression, and then we can predict our epsilon statement. Now, we're going to let x plus 2 be less than delta, and we're going to substitute epsilon over 4 in for delta. And so we'll get absolute value of x plus 2 less than epsilon over 4. And we will multiply both sides by 4. That'll give us 4x plus 2 less than epsilon. And because when I distribute a positive inside the absolute value, it will not change what's on the inside of the absolute value, I can distribute. And that will give me 4x plus 8 inside absolute value, which is less than epsilon. And here we should note that 8 is equal to 5 plus 3. So we can rewrite this as 4x plus 5 plus 3 less than epsilon, and thus f of x minus the limit is less than epsilon. And our proof. All right, now I know that that one's kind of tough and not real easy to understand, but if you follow the form, and there won't be any on my quizzes that are any harder than that, you should be okay. The next example, find the limit numerically by filling in the table and check. All right, so we have this value right here, we have this expression right here, and we're going to want to make a table for this. All right, so let's use Desmos. So here we are in Desmos, and we want to make us a table. So the first thing we're going to do is we're going to type in that function. We'll go f of x is equal to, we'll put parentheses around it. So we'll go x minus 3, and then we'll go divided by, and we'll go x, and then we'll go shift up arrow to get our squared in there. Press our right arrow key, and and hit -9 parenthesis there, and we want to make a table. So we're going to come up here, we're going to add an item, we're going to add a table, and we're going to delete that little 1 from down there, and we're going to change this to f of x, and then it should allow us to do everything. We're just going to type in from that table. We're going to go 2.9, we'll hit enter, 2.99, we'll hit enter, 2.999, we'll hit 3, then we'll hit 3.001, 3.01, and then 3.1. And we'll round to, let's say, let's take a look at those. We'll round those to 3 places, and just so that you can see this a little bit better, we'll change it to projector mode. So at 2.9 we have 0.1694, which will round up to 5. We have at 2.99 we have 0.16694. At 2.999 we have 0.16669. At 3 we have undefined. At 3.001 we have 1.666668. At 3.01 we have 1.638, and then at 3.1 we have 1.639. And you can see by looking at this area right here that as I come in from the left and I come in from the right, these values all tend to point to a single value. So let's go back and fill in that chart. And here at 2.9 we have 0.1694. At 2.99 we have 0.16694. At 2.999 we have 0.16669. Here we have UDF, it's undefined. Here we have 0.16663. Here we have 0.16638, and here we have 0.16393. Now, again, this method you'll see from time to time, but we're just making a guesstimate here, and it looks to me like I'm getting closer and closer. Each time it's 1.6, and then I get 1.66, and then I get 1.666. If I were guessing, I would say that we're going from 0.16 repeating, because each time we get 1 decimal place closer, we're adding a 6. Now, 0.16 repeating, that thing is equal to just 1/6. So for the sake of this discussion, I am going to say that this is equal to 1/6. Okay, for our final example, we're going to use the graph of the function to find the limit. So here we have a piecewise function where and we're trying to find the limit as f of x goes to 1, where f of x is equal to x squared plus 3 when x is not equal to 1, and 2 when x is equal to 1. So we're trying to find this limit as it goes to 1. So we're looking at the x equals 1, and clearly this function was meant to have some issue at that point. So as a piecewise function, we can graph that in decimals. So I've set this up already, and this is what that graph looks like. At x equals 1, this is 1 right here. We can see it. The function equals 2. Everywhere else, it equals this parabola. Now, does this limit actually exist even though the point is down here? Well, if I follow this in from the right-hand side, it tends to look like 4. And as I follow it in from the right-hand side, it tends to look like 4. Now, there are a lot of algebraic things that we could do to come up with this, but this one says just use the graph to estimate. And so what we're going to do is we're going to estimate it by saying as we come in from the left, it points to 4, and as we come in from the right, it points to 4. That's what we're getting. So if I go back to here, we're going to say that the limit as x goes to 1 of f of x, and this is our f of x, is going to equal to 4. All right, well, that's all I got for today, folks. So the Star Wars fun fact of the day. Kenny Baker was a little person who played inside the R2-D2 suit back in 1976 because robotics at that time were not good enough to do everything that George Lucas wanted the robot to do. It is rumored that Kenny often did such a good job at playing a robot that he would often be forgotten in the suit when the cast broke for lunch. Not very nice to do to a little guy. Well, that's all I got for today, folks. Have a good day. Goodbye.